All right. So today is Wednesday, March the 12th, okay? So let's look at these. So if I'm looking at this half cell, okay? A voltaic cell, that's a battery. All batteries are voltaic cells. They're also called galvanic, thank you. I was having a little senior moment. A galvanic cell named after Luigi Galvani. Okay, so we have this, and you have it in front of you. It didn't copy real well here, but we have a silver nitrate, iron nitrate, piece of iron metal, piece of silver metal. So you always kind of have those in your solution. So they give you your half cells. Right? I mean, the cell potential's right there. They're not going to give you the big table like they showed in the textbook. They're always just going to give you the individual reduction potentials. Okay? So when I'm looking at this, and I see these values right here, the net ionic equation is going from silver to iron. Sometimes they're going to ask you to write this net ionic equation. All right, that's very common in free response questions to have to write the ionic equation. First things first, how do I know which one's going to be reduced without this net ionic equation? Without that, just looking here, how could I tell which substance is going to be reduced, which is going to be oxidized?
Which one's positive and negative?
Sometimes they're both negative though. But it has to do with that. These are the reduction potential. What does that mean, reduction potential?
How much the charge can be reduced on each thing.
Okay?
Gaining electrons.
There you go. So that's the words I'm looking for. Say that again.
They want to lose electrons.
When you're so close. So what?
How much they want to.
How much they want to reduction potential is gaining electrons, not losing. Because somehow or other, you've got to get this into your algebra. The gaining and losing, oxidation reduction, and endo and exothermic. Somehow or other, you've got to work those things out in your brain. I can't get inside your head and fix that. Okay? I've tried. Okay? Now, so which one, the reduction potential, the thing that wants it the most, the bigger the number, the higher, the more positive the number, the more it wants to. So if they had two negative numbers, the one that's closer to zero, the more positive value, even if they're both negative. Okay? The one that has the greater reduction potential is the one that's going to get reduced. It's got the greatest potential to be reduced. Okay? So in this case, this is obviously greater reduction potential than this. So I know that this reaction, based upon this, the fact that this number is bigger than this number, I know that this one's going to go this way, but this one's going to get oxidized, so this one's going to go that way. Now, I am gaining 2 electrons, but I'm gaining 1 electron, I'm losing 2 electrons. So what would I have to do in this here to make electrons gained equal electrons lost? To my half reactions. Here are my 2 half reactions. I have to multiply this one by 2, so I get 2, 2, and 2. So now my electrons are going to cancel. So when I go then and look at they give you the balanced net ionic equation, that's where the 2 comes in. Okay, because just Ag plus Fe goes to Fe to Ag. By itself, it's 1 to 1, but we're balancing the charge as well. So we only have a +1 and we have a +2. So we have to balance the charge. So that's kind of our half reaction. That's why we learned the half reaction method. So we can kind of see how that works like that. Okay? Now they gave you that, but this is how we would know. So now that I have it written, this one's going to go this way. This one, the oxidation is going to go the other way. But what's the standard reduction potential? What's my E cell going to be? What's the simple equation to calculate E cell?
E reduction minus E oxidation.
E cell, and I'm just going to write it up here. E cell, and standard simply means at standard conditions. Okay, that's the 25 degrees Celsius, 1 molar, 1 molar. Okay, it's always going to be equal to E red minus E ox. So we have to know which one's being reduced, which one's being oxidized. The one with the greater reduction potential is the one that's getting reduced. in here. Now, the good thing is it doesn't matter what the coefficients are or anything. And so we can just simply say 0.8 minus the negative 0.44. And what's that gonna equal? 1.24.
Yeah, that's what
Okay? I mean, that math is super simple.
Is there a way to like, do we have to know eventually like how to figure out?
The 0.8 and the 0.44?
Yeah.
No. It's always given.
It's always just.
Yep.
given.
I mean, I'm telling you, this problem, that's as hard as it gets. As long as you remember redox, E red minus E ox. Okay? Now, the next one, how do we change this voltage? We can change the concentrations of our cells. If we change these. Standard conditions, this is 1 molar and 1 molar. That's standard conditions. That's when you're gonna get this.
So you said it's just the absolute value of like all the, because it's in volts, right?
Yes.
So it's just the absolute value of total voltage?
Well, it all depends, but you gotta subtract it in the right way.
Well, so sometimes the oxidation is positive?
Yes.
Okay.
Okay, because sometimes they're both negative, sometimes one's negative, one's positive, they could both be positive, so the signs vary. So it's always just E red minus E
How can
ox.
it be positive? Because isn't it, well, okay.
Because the reality is that the oxidation potential of this is actually positive 0.44. So some books teach it E red plus E ox.
Yeah.
But you gotta change the sign for the oxidation to positive.
So oxidation is always positive in the,
No, it's always the opposite of whatever the reduction potential is. Okay?
okay.
So you can't with these values, because they're all just compared to hydrogen. Hydrogen's the reference electrode, hydrogen's 0, so it's all compared. How much do they want to gain an electron compared to, they want to do more than hydrogen positive, less than hydrogen negative? We've got 2 of them that are less than hydrogen, they're both going to be negative, but different values of negative. If they're both greater than hydrogen, they'll both be positive, but different from one another. So it's always just E red minus E ox.
Okay.
Don't complicate it any more than that. Okay? So that's number 4, super easy. But again, I want us to know that when we're writing, if we in a free response question have to write the balanced net ionic equation, the oxidation is always going to be the opposite direction. Everything's always written as a reduction potential. But in any redox reaction, one thing gets reduced, the other thing gets oxidized. And so the thing that has the lesser reduction potential is going to get oxidized, it's going to go the opposite direction. And then you balance your electrons. Okay? Alright, so now let's look at the flow of electrons. Okay, we got to keep all that, and unfortunately it's on a separate page. Okay? So here's my setup. Okay? Well, okay, so we got these 4. Well, let's just go back. Actually, I'm going to go back to here. I have this setup right here. So let's just determine, without even looking at my answers, let's determine what way are the electrons and the ions going to flow. They're going to go from what to what? Okay? They're going to go from the thing, okay, that's being reduced, pardon me, the thing that's being oxidized is what's losing the electrons, so they're flowing from the thing losing the electrons to the thing gaining electrons. Okay? So, again, the iron is losing, so the electrons are going to originate from here, and the electrons are going to flow this way. And flow to this. Okay? So what's happening to the negative charge here? This is becoming negative. Okay? As electrons flow in here, this becomes negative. So what's attracted? Because again, remember, we have Ag plus and NO3 minus in here. We have Fe2 plus, and we have NO3 minus in here, 2 NO3 minuses in there. So as electrons leave, what's happening to the iron here?
It's adding to the solution.
Okay, it's going dissolving, right? It's becoming Fe2+. So the iron is coming into the solution. So the Fe2+ is increasing. So how do we balance that out? Because we're right now, just Fe2+ is coming in, but all solutions have to be neutral. So what has to happen? More NO3 minus has to come in to the solution. So notice the flow of negative here, and so the NO3s are going to come up in here. Okay, so what's going to happen here? As this becomes negative,
The silver's gonna solidify.
the silver is going to solidify on the electrode.
Yeah.
So this electrode is going to get heavier. This electrode is going to get lighter. What about the total mass of the system, though? It stays the same. It's closed. The total mass of the system stays the same. It's just the iron is going to be losing electrons, becoming aqueous. The silver is gaining electrons, going from aqueous to solid. And it's all going to occur on the electrode, because that's where the electrons are. Okay? So it's just going to be this flow. So what's going to happen to the Na pluses? If they were to ever ask that, which way are they flowing?
No way, dude.
As that plus leaves,
They're going into
the Na pluses have to be going into here to replace, because everything has to remain neutral. So the function of the salt bridge is to simply allow ions to flow to maintain electrical neutrality. As things get oxidized, they come into solution, so the positive on one side starts building up. If we didn't have the salt bridge, positive builds up, negative builds up, and then everything stops almost instantly. That's why we saw no current without the salt bridge. With the salt bridge, the ions can flow. They're not doing anything, they're not gaining or losing, they're spectator ions, but they're maintaining electrical neutrality is all they're doing. Okay? So which diagram shows that on the next page? Is it D that shows that? Okay, so we should have electrons flowing from the iron to the silver. So I'm gonna leave this picture up just to verify. So then we go when we look. Does D match that? Okay? Yes. Okay, the electrons are flowing from the iron to the sulfur. Notice they don't have anything in the salt bridge. Okay, do they ask a question about that? What is the function? So let's go ahead right here, number 8. What is the function of the salt bridge? So what's the answer? B. Donates ions to keep the solutions at the electrodes electrically neutral. That's its goal, to maintain electrical neutrality. That's a commonly asked question right there, both free response and multiple choice. Okay? So a lot of times they'll draw the voltaic cell, but they won't put the salt bridge in. They'll ask what piece is missing and what's its function. You know, a 1 and a 2 under A. You know, given the diagram, what is needed, you know, to complete the circuit, salt bridge, and then B, what's the function of the piece that was missing to maintain electrical neutrality. Okay? All right. Now, let's jump ahead and learn something new. Which of the following starting concentration values for each solution will produce the highest cell potential? Well, what happens if we're not at standard conditions? Okay? What happens if we're not at standard conditions? And we have what's called the Nernst equation. Okay? To where we find your E cell is going to equal your E cell at standard conditions minus, and I can never remember it. Let me see your book right here. It's given in the equation sheet. RT over NF natural log of Q. Good old Q again. Okay, now for multiple choice question, you don't really have to be able to plug values into this. But what do you think R is? That's your gas constant. Okay, but, okay, temperature is Kelvin. What's N? Moles. And in this case, it's total moles transferred. Okay, so between the 2 Ag plus going to Fe, how many moles of electrons are being transferred? How many moles are being gained or how many moles are being lost in our balanced equation that we did previously? Yeah. Well, in our net ionic equation, or when we just did oxidation reduction, what was the total number of electrons gained and the total number of electrons lost that canceled out? Somebody's just said it. 2. Okay? It's whatever, when you do your half cells and you multiply to get electrons gained equal electrons lost, it's the total value after you multiply. Now, it doesn't matter. It's either electrons gained or electrons lost because they're going to equal one another. So the iron went from 0 to plus 2. So I know the N is going to equal 2. All right? Silver went from 0 to plus, but there were 2 of them. So the total is plus 2. Okay, so N is going to equal 2. N is the number of electrons gained versus electrons lost. F is called the Faraday. It's kind of what today is. It's a Faraday. Named after Michael Faraday. Like a Faraday cage. Okay, all about electricity. It's a constant. It's given in your equation sheet. It's equal to, most people just say 96,500, but it's 96,485 coulombs. Come on, I'm gonna have a serious senior moment here. Is it coulombs per second or just coulombs? Coulombs, oh, I know it is. Coulombs per mole of electrons. Okay? Eventually it comes to me. Just a little bit slower these days. So if we have if you take 6.02 times 10 to the 23rd electrons and put all of their charge together, add up all the charges of each of the 602 sextillion electrons, the total charge is 96,485 coulombs. That's the total charge of a mole of electrons. And that's going to be important when we go the other direction and do electrolysis. Okay, so that's what you would plug into here. T and R is your gas constant. Okay, so we're going to come back. When we look at this, I don't need this. Remember, Q is equal to products over reactants. Now we just need to know about logarithms. If Q is a whole number, in other words, if products are greater than reactants, what does that mean about the log of Q? Is it a positive or a negative number? It's a positive number. The natural log of a number greater than 0, or greater than 1, I should say, the natural log of a number greater than 1 is a positive number. If it's greater than 1, the logarithm, whether it's natural or common, it's going to be great. It's going to be a positive number. If it's a decimal, it's going to be a negative number, right? All of these things are positive. So if products are greater than reactants, then Q is going to be a number greater than 1. So this whole thing is going to be a negative term. Okay? Right? If it's greater than 1, isn't the natural log of what's the natural log of like a number 5? It's a positive number. Did I say negative number?
Yeah.
It's going to be a positive number. That's what I said. Okay? Q is going to, if Q, let's try this again. That's clear. I'm locked in. I've just got to make sure, I got to fix what I just messed up. So I'm clearing the data. Okay? Let's just say 5 over 1. Making up numbers. We have more product than we do reactant. This is gonna be a positive number, which means I'm gonna subtract a positive number. This is my E cell, this is my E red minus E ox. So if I have more products, and it's logical, I'm gonna have a lower E cell. It's gonna subtract from this, my E cell is gonna be going down. When batteries start getting used, and they go from left to right, from reactants to products, as you get more and more products, does the voltage of your battery go up or does it go down? It goes down. So as products increase, your cell potential, your battery cell voltage goes down. On the other hand, if we have 1/5, now we have a decimal. So the natural log of a decimal is going to now be a negative number. So now it's going to be minus a minus. And that's where your battery starts. When you have more reactant than you do product, and so as a result, you're going to add to it and your cell potential goes up. So it's all based upon Q. Now we can figure out those actual values, but they don't really ask you to do that very often anymore. They want it more from a theoretical point of view like this. So just knowing Q, if you have more reactants, your cell potential is going to go up. If you have more products, cell potential goes down. This E cell right here is when you have 1 molar and 1 molar, standard conditions. If you're at something other than standard conditions, usually it's changing the concentration. Then you just look at, do I have more products, do I have more reactants? So I can come now just knowing that basic fact. This equation is in your equation sheet, so you'll always have that equation. It's called the Nernst equation. So if I look now at number 5, number 6, which of the following concentrations, okay? So again, remember my equation is 2Ag plus Fe solid goes to 2Ag solid plus Fe2 plus aqueous. So the only things in my Q, remember, are these two things. Solids aren't in my Q. So, which one am I going to have? I want the highest cell potential, so what do I want the most of?
Reactant.
I want most reactants, right? So I want the highest concentration of reactants, the lowest concentration of products. I want that Q to be the greatest, the smallest decimal, I guess I should say, the smallest decimal. Okay? So I have Ag plus, I want that to be 2, so obviously I can cancel those out. All right? So I want the greatest reactant, I want the lowest product. Do you understand that mathematically? Okay? And it makes sense logically too, and just think of a battery. Remember, a voltaic cell is a battery. Okay? You want to have a lot of reactant, you don't want product. That's a brand new battery. But as the battery goes, you have less reactant, you get more product, the battery starts losing its cell potential. Now the wonderful thing about an alkaline battery, which is what all of your normal Duracells and Energizers are, and I'm not sure the chemistry behind this, but with an alkaline battery, the voltage stays, and then when it's dead, it just drops. Before they came out with alkaline batteries, they were actually acid-based batteries, just the normal battery. And that was back when we had the Sony Walkman, the tape player with the cassette tapes that we'd wear on our hip, you know, but immediately as the batteries started wearing out, it just gets slower and slower and slower and slower and slower. It would die a slow death. Kind of like flashlights. Sometimes you can tell on a flashlight it's just not quite as bright as it used to be, you know, but with alkaline batteries it's more, and then they just drop off, okay? But again, it makes sense. The more reactant you have, the higher the cell value is going to be. The more product you have, the more dead the battery is going to be.
What did you say N was again?
Moles transferred. In this case, again, this is going from 0 to +2, so I know that we're losing 2 electrons. This is going here, I'm gaining 2 electrons total. It's the total number. It's after, again, remember when we did the half reaction, you got to make sure electrons gained equals electrons lost. We had to cross multiply or make the two equal one another. It's the total number after you multiply your half cells. Okay? Total number of electrons transferred, that's what N is.
You mean total like
So the-
2 or total like 4?
No, it's not, it's either gained or lost.
Okay.
Those numbers equal, is the total gained or the total lost, it's 2. Okay? So you only have to look at one, you either look at the oxidation half or you look at the reduction half, whatever the number is, that's your N. Okay? So we can just do, this is more of a, once you understand this, there's really no math involved in that, and you can figure out logically, it's just, again, most reactants, fewest products gonna give you the biggest cell potential. Well, that's 6, what does 7 ask for? Oh. Alright, 7 is a plug into an equation. And 7's gonna take us a flashback to something that I meant to go over in the last chapter, and then I ran out of time and I had to take it off the test. Alright, we have a relationship between K, G, and E. Alright, so we have K, G, and E. So I showed you the equation that delta G is equal to negative RT natural log of K. I threw that out for you, and we barely talked about it, but I really wanted to do it. I think it was a bonus on the delta, on the, yes, yes. Is it 45? Good, yes. Now, so that's the relationship between delta G and K. All right? Delta G and K. The relationship between delta G, negative N, F, E. Okay? Negative N, F, E, where N is the moles of electrons transferred again. There are 2 R's in transferred at the end, aren't there?
I think so.
Or is it just one? I didn't let that.
Is the E cell?
Yes.
Okay.
Almost all we do everything is standard, because delta G, everything is standard. Okay? F is the Faraday. Did anyone look up? Are there 2 R's? I don't know why that one's. It's the Faraday. Again, that's just the constant. And E is your E cell. Now again, let's talk about when is the reaction spontaneous with what sign of delta G? Negative. So what does that mean about the sign of E for spontaneous reaction? Has to be positive. E cell has to be positive for the reaction to be spontaneous. E cell must be positive for a voltaic cell to operate. You cannot have a battery with a negative E cell.
That means it's dead.
It's dead. Okay? So E cell, so that's why it's got to be red minus ox. It's always going to give you the positive value. If you get a negative value, well, I'm not going to say that because sometimes they purposely give you the negative and then they ask if the cell will work or whatever. But E red minus E ox. Okay? Now, what does that mean about K as well? All right? If I'm going to take the natural log of K, when is the only time that it's going to be positive to make delta G negative? What must be true about the value of K? It has to be greater than 1. So what type of reaction is that going to be? A reactant or product favored? Product favored. Remember, a K is products over reactants. K has got to be greater than 1. So then log of K is positive. So delta G is negative. So we need to know, so K must be greater than 1. Product favored. See, it's all coming together now.
So K is like Q in this.
K is Q. Q is it's just not in equilibrium, but K and Q are calculated exactly the same way. Q is not at equilibrium, K is at equilibrium, but products over reactants. Exact same thing.
So, never mind.
Well, so let's just put this then in a nutshell then. For a spontaneous reaction, we're always going to know delta G is always going to be what sign? Negative. K is always going to be greater than 1. Greater than 1. And E cell is always going to be positive. Those are your spontaneous reactions. Those things are the things that have to be true for it to be product favored. Okay? Now, so what is true about the values of K and Q for this cell? Well, is the cell positive? It was the E cell positive that we calculated in what, 6 or 5 or wherever it was. Yes. So E cell is positive. So what does that mean about delta G? It's negative. What does that mean about K? Greater than 1. Okay? It's greater than 1. Okay? It's not necessarily less than 0. It's got to be greater than 1. So which one says that? So K has to be greater than 1. So the only one where K is greater than 1 is D. So you don't even have to, and by the way, when you have these multiple questions, and this is an ACT type thing too, when you have a question asking multiple things, take one at a time. Okay? So here you have K and G that you got to deal with. We'll just relate E to K first. Okay? I would probably even do E to G because it's easier. If E's positive, G has to be negative. So I know that G has to be less than 0. So I can eliminate this one and I can eliminate that one right off the bat. Okay? Then I just have to worry about the K. K has to be greater than 1 in order for G to be negative.
You said G is always negative, right?
No.
Oh, wait, what?
For a reaction to be spontaneous, for a reaction to occur, it has to be negative.
Yeah.
Okay, but if it's positive, that just means the reaction wants to go the other way. It's not spontaneous at standard conditions. What time is it right now?
No, we got we're done in 2 minutes.
11:52. It's broken. I have another one. Ordered yesterday, just like it. I've changed the batteries out. It's not the battery, it's the clock.
So it's a negative.
Yeah. No. Yeah. I'm about to watch time fly as I throw the clock out the window.
Can we do that right now?
Can we go
Oh wait, that'd be so fun, yeah.
Yeah.
That is so
We'll video it from down below.
Yeah, well, yeah, Dr. E's office is right below mine, her door, so when she's walking out
Oh,
to,
Graver. I don't know Graver's one day.
yeah, I can throw it at Graver's car if he's still got his Geo out there. He couldn't tell the difference if it hit it. And so. All right. So that's the gist. That's the gist of everything voltaic for a voltaic cell. Okay, we need to be able to calculate E cell, just E red minus E ox. We need to be able to show the direction that the electrons are going to flow, and they're always going to go. Oh, by the way, no, one last thing we got to label. Okay. We have to always know the definition of the anode and the cathode. Okay, so put this somewhere in notes. Anode is where oxidation takes place. Cathode, obviously, then is where reduction takes place. The way I remember it is the vowels stay together, the consonants stay together. Okay? So the anode is always defined as the electrode where oxidation is taking place. In this cell, which cell, the iron or the silver, is the oxidation taking place? In the iron. So the iron would be the anode, the silver is the cathode. Okay? Just remember, vowels go together, consonants go together. Anode, oxidation, cathode, reduction. Okay?
Like oxidize our AO, like to get away.
Yes, that's exactly right. Whatever it takes for you to remember. He's gonna go to counseling the rest of his life over this AO thing. Of all the struggles that we have in the world. Free AO! He's gonna start bringing signs in the hallway, protesting, free AO!
Hey, bro, can we look for
All right, hey look, this is just memorization. Easy money, but just memorization. Anode is oxidation, cathode is reduction. That's how it's always gonna be defined. All right. Now, this is one that was on the test last year. It was the last free response question on last year's test. And everybody freaked out and said, oh, Mr. Hobbs, you never taught us this. And I did.
It's interstitial.
Okay? So, stainless steel is primarily made up of three elements, iron, carbon, and chromium. Which of the below diagram accurately represents the stainless steel on a particular, okay? So, how are iron and chromium in terms of size?
About the same.
24 and 26 are going to be about the same, right? So iron and chromium need to be about the same size, okay? And where the, notice, so what type of alloy would the iron and chromium make? No, that's the carbon. Iron and chromium, where is it? Iron, iron, well, B. Oh, there's the chromium. I couldn't see any chromiums. Okay, what type? If the carbon wasn't in there, what type of would it be between the iron and the chromium? What's it called?
The ones that are next to each other.
What? There are two types of alloys. Okay, yeah.
Wait, so I said interstitial.
Inter-
That was one of them.
Stitial.
Well, you're technically right because of the carbon.
Okay, that's your carbon.
That's all I remember.
That's that one.
And it's also
Okay.
B is
It's also here. It's this one too. It's when the carbon, the smaller one, fits into the little interstices, the spaces in between here. But what's this? Since they're about the same size, what type of alloy is it? Nobody remembers?
The same size alloy.
Okay, it's kind of going in place of it.
Stainless
It's a
steel.
substitutional alloy.
I said so. Okay, I said that on everything. I said that. No, I was just trying to remember. I didn't know which one was which.
Yeah. Okay. I never heard the word, but
There was no confidence in it. So
Okay.
I don't
okay. Substitutional. Okay. So you sub in equally. They're the same size. Interstitial is the little spaces in between that you put the smaller one in. So if two different ions or two different atoms are about the same size, there would be a substitutional alloy. And if they're one's significantly smaller than the other, it would be an interstitial.
So it can be both.
This one would be both.
But is that common? I know stainless steel, but like, is that common?
Probably.
Okay.
I don't really know hardly anything about alloys.
You don't-
And they don't ask hardly anything now because they're so diverse as far as the characteristics. Does it make it harder? Does it make it more malleable? Does it increase this? Does it decrease that? So when they first came out with that, they tried to put some things that, and then
Or like
other
guaranteed,
professors
yeah.
started arguing, saying, wait, this does that. So they've kind of really minimized it to just
Stainless
definitions.
steel.
What definitions of same size, smaller size. What this question is really asking you is, do you know periodic trends on size? The fact that chromium and iron are about right next to one another, so they're going to be about the same size. Matter of fact, all your transition metals, because they all have the 3D 4s, they all have that 4s electron out there, they're all about the same size. Okay? So you're adding core electrons when you add the 3D, so you don't really get much difference in size. So if there's ever a question about which of them are nearly the same size, transition metals are the ones that are in the same row are going to be about nearly the same size. Only in the same row. Okay? As you go down, they always get bigger. Okay, so that was just kind of a review, so you can't get mad at me, because now you're gonna remember that that was there.
Thanks.
So this was the other one that I had on the board. And I asked 2 questions about this. Okay, this is straight up memorization.
What happened?
She just got herself caught in her 3-ring binder. That hurts like the dickens.
The what?
What?
The
The
what?
what?
How old are you?
The Dickens?
I don't know where that comes from. That's just what old people say.
The Dickens?
Yes.
What does the
Now, don't nod your head. You know what you did.
That's
No, it's just, he was called the Dickens.
it's an old expression.
Right.
Anyway,
Not me, Mom.
but you know, we didn't take everything into the gutter, Simone. Okay.
I mean, I was starting to get.
All right. Light in which region? Now look, listen, if you did not write down the things that I had on the board, okay? Somebody, you need to get them from somebody, okay? But microwaves, what do microwaves? Rotational, and you can always remember that in terms of a microwave, always has a plate that rotates on the inside. But they measure the rotational energy of molecules, okay? Ultraviolet is the one that deals, and visible light deal with electron transitions going up and down. So anything dealing with electron transitions, light being given off, the spectrum, EMR, all that. And infrared deals with the type of bonds, the double, single, triple bonds. And so you have IR, and you can kind of tell the structure of a molecule based upon its infrared signature. Okay, so light in which region electromagnetic supports the hypothesis that the NO bonds in the nitrate are longer than those. So that's pretty much going to be your infrared, okay, because it's going to measure the type of bonds. Again, a very small chance at one question generally at the most on something like that. But that's straight up memorization again, okay? But those are the little things that I do want to kind of memorize. Gamma is just a type of radioactivity. It doesn't really have anything to do, you don't measure anything with that. Okay, so now here's a PEZ spectrum. You remember PEZ?
Yes.
Okay, so what's this first hump represent?
1S2.
1s, and the height tells me it's 2. We always know 2, 1s2, we always just know that. So that tells me the reference point. Height tells me how many electrons, okay? The closest one's always the first energy level. This is the nucleus here. 1s2, 2s2, 2p6, 3s1. And I know 3s1 is going to be which element? Sodium. Okay?
That's a given.
I know the 2 dashes right there mean there's a big distance.
Yeah.
But why is there one?
Okay, because remember, there's a big energy difference between the first and the second energy level. Okay, so that energy, if they were just to kind of go from there, because when we drew it out, here's your 1s, your 2s is here, and then your 3s, there's a smaller, the energy levels start getting closer and closer the farther out you get. And that's the mathematical, because the energy of the cell, energy of the electron on that first energy level is negative 2.18, 10 to the minus 18 divided by n squared. So this is going to be divided by 1 squared. This is going to be divided by 2 squared. So it's a difference of 4. This one's 4 times more energetic than this one. But then this one is going to be divided by 3 squared. So now we're going from 4 to 9. Instead of going from 1 to 4, that's 4 times. Now we're going from 4 to 9, which is only 2.5, or 2.25.
Is that a big energy jump? Like not the same between like the second and third? There's like no dashes.
Right, because, again, now you're going from 4 to 9, so there's not as big of a difference between the energy levels.
No, I'm talking like that's
Here, yeah.
No, from that 2p6 to 3s1.
Yeah, but there's still no dash. The only dash is right, that's the only mean one that tells me that it's a big jump,
Okay.
okay? And that's, again, because it's 4 times difference, whereas this one is just over 2. And then when you go to the next one, is 4 squared, so now we're going from 9 to 16, now it's not even 2 times the difference. Okay? Alright, so let's take a 5-minute break. Okay? Go, check all your, make sure how many likes you got on your latest post. Okay? Go get water, go to the bathroom if you need to go to the bathroom, do all those things, pause the video, top left corner. All right, so here we go. So if I'm looking at this question, which is number 14, given this graph, this is another gimme question if you just know the graph. Do we remember where is the bond length going to be, or the lowest potential energy? At which point interaction between the two nuclei is strongest? No.
C.
C. It's always going to be at the bottom of the well. Okay? That's where the potential energy is the lowest. That's where here they're too far apart. So you have one atom is here. And this is the distance between the nuclei. As this atom is approaching, there's no attraction. Now the attraction starts getting more and more and more and more. You have the greatest attraction. And then as they start getting closer, now the nuclei begin to repel one another, and you get lesser and lesser attraction. So you always just want the bottom of the well. So another question would be, what would be the bond? I think we did one of these on test or on a practice, maybe on a Princeton review or something. What's the bond length? It's going to be this distance is the bond length, whatever, but it's not labeled on this one.
The book said that
Yeah, the book
they have
says
the most
A.
interactions at A.
I knew I was right.
Potential energy's the highest.
Well, are the interactions between the two nuclei, well, they're talking about repulsive force. They're never going to ask that. They're always going to ask where it is going to be here. Okay, that's a stupid question. Okay, I'm
You
100%.
got it wrong. You got it wrong.
Well, no, I'm 100% sure. I'm 100% sure that they're going to ask on an AP test where the attraction is. That's where the attraction between the two atoms are going to be the greatest. The attraction. They're saying interaction because the repulsion is going to be the greatest there, because it's the highest positive. But AP only questions I've ever seen are at the bottom of the well. Is where tell me where the bond length is going to be. This is where one nucleus is going to be here, the other nucleus is going to be there. That's where it's going to be a vibration back and forth between these 2 points. So, regardless of what that question's asking, that's what you need to know. Now, we look at, we don't know anything about these acids and bases. This one here, what's the only difference between the equations?
Double
Doubled
and reverse.
and reversed, so you go 1 over k squared, right? So we already know how to do that. We don't have to explain that one. Those are all just basic things. So if I look at this number 24, how do you know how to do 24? I have KP.
Calculate Q.
Calculate Q. All right? So what's Q going to equal here? What over what? It's going to be O2
Plus the pressure of NO2.
not plus but times
Time.
to the 4th over the pressure of N2O5 squared, right? So we're just going to plug in, and you end up getting the O2 is 0.2. The NO2 is they made that one easy, 0.1 to the 4th, and the N2O5 is 0.2 squared. Now you do have a calculator. This is the second year you're going to have a calculator allowed on multiple choice. So what does that come out to? To me, one of the 0.2 is going to cancel, so you're really just dividing 0.1 to the 4th divided by 0.2, which comes out to what? 0.005. So Q is less than K. Now, y'all, in looking at different things that y'all have done, some of y'all go and calculate Q, and then you look at something like this and you say Q is greater than K. You get your greater than and less than's backwards once you went and calculated it. Okay? So make sure that we understand the greater than less than part. So since Q is less than K, what does the reaction have to do? Now, so we're at initial, we're not at equilibrium here. Okay? So we gotta think, so now how does the reaction have to go to get to equilibrium?
Shift
Shift
left.
left.
Shift right.
Right, there being more product.
Right.
Shift left.
It's products favor.
Q is less than K. I need to make Q bigger. It's products over reactants. So right now, Q is less than K, so if you have too many reactants, not enough products. So I need more products. I need Q to get bigger, to equal K, to get back to equilibrium. Okay? Somehow or other, you guys mess this all up in your head. It's just basic division math, decimals. So it's got to shift to the right. It's got to go right to get to equilibrium. So now it's going to say the N2O5 then is going to decrease, right? Well, this is the only one it can be. Only have to look at one of them. Don't try and get them all three at once. Just take one at a time. But the other two have to increase because it's going to be shifting right. No, those should be now this one's harder because you have to actually calculate Q. Now, how did I know to calculate Q? I'm given K, I'm given initial concentrations, and I'm given K. I'm given all three initial concentrations and K. That's my clue that it's a Q problem. All right, this one just goes back to straight line, okay? It's second order. So second order is 1 over what?
The molar.
1 over it's got to be a 1 over the concentration, right? Okay. Now, again, let's just say that you forgot.
Equation.
Okay. So you go to the equation sheet. You go to the equation sheet where it says kinetics. You go to your equation sheet. What is this the equation for?
0 or
This is 0, this is first, this is second. So this is what your y-axis is going to be. Concentration, natural log of concentration, 1 over concentration. Okay? So you look for the straight line. Whichever one of the y-axis gives you the straight line, you have that one. Sorry, I keep losing my page. All right, I gotta do 1 or 2 more. I'm going to review the 35. Here's my reaction. First off, delta H is positive. Does that mean it's endo or exothermic? Endothermic. So does that mean products need to be above or below reactants? Above. Okay? So that means that I can eliminate A and B. If I just know it's endothermic. But does this one even?
That's good.
So there's increased lines.
Yeah, nah.
What is that?
Okay?
It goes all the way up to
Yeah.
Okay? Now, is the delta H on this one right?
Yes.
Yeah. Okay, but what's wrong with EA?
It doesn't go all the way down to the starting point.
Okay, this actually is EA for the reverse reaction, just FYI. It's from here to here is EA for the reverse. Okay, this is going to be your EA for the forward reaction.
Maybe a dumb question, but for delta H, for the reverse, it would go all the way up to the crest, right?
No, it's still delta. It's just the difference between reactants and products.
Okay.
It's just going to be negative versus
Yeah.
positive.
Okay.
Now, what if, in terms of kinetics, what if in this reaction we had CH4 going to CH3 plus an H plus, how is that going to go to HCN? That's a crazy one. Plus,
Is it
H, CNH, and then HCNH goes to HCN plus H2. Now, I know that they don't all balance out or whatever, but let's just say it did that. What's my potential energy graph? And let's just say that this one is slow. Slow is SL, Steve. S slow, and this one's fast. What's my energy diagram gonna look like on this one?
You have the two,
Say what?
you have like the two hubs.
I'm gonna have to have two peaks, two humps. Which one's gonna be have the greater EA?
Slow.
The slow step. So it's gonna look more like, even if it's endothermic, it's gonna look like this. More like that. So my first EA, this is my first EA, this is my second EA, this is where my intermediates form. Okay? So just kind of as far as potential energy diagrams go, you need to know that if there were 3 steps, you'd have 3 humps. The biggest one, the biggest EA is always the slow step. So if the second step was slow, it would look more like something like that. Okay? All right, just since we're reviewing. All right, here's a complicated Maxwell-Boltzmann temperature distribution graph. Okay, X, Y, Z. The velocity distribution of 3 different gases. Okay, here's your velocity distribution of 3 different gases. Which gas is going the fastest, X, Y, or Z? Z. Does everybody know that Z is the fast? It's not the height of the curve, it's how far to the right, because that's the one that's measuring velocity or speed. Okay? So the velocity of 3 gases plotted, which gas belongs to which distribution? Okay? So, fastest is Z. Is that going to be the heaviest or the lightest?
Lightest.
If you have a big mass, you ain't going fast. Okay? So Z is the lightest, X is the heaviest. So we know that Z is going to be hydrogen. Okay? So it's got to be one of these two, because hydrogen is always the lightest. Nothing gets lighter than hydrogen. Okay? So between these then, you have 18 and you got 28. So nitrogen's the heaviest, so it's got to be X. Water is 18, the water vapor is 18, so it's going to be the middle. As much as we've gone over as Maxwell-Boltzmann temperature distribution graph, that should be easy money too. But I see a lot of y'all making changes and making notes on this one, so. I don't really quite understand this question,
Neither did I.
okay? Which gas would exert the greatest pressure afterward? I guess but the valves are closed, so we're just in here. So 12 grams of water is what's the pressure gonna be dependent upon? Moles, right? 12 over 18 is 2/3 of a mole. So it's like 0.67 over 1. So 0.67 molar. Okay? 14 grams of N2. Well, N2 is going to be 28 grams. So it's at 0.5 divided by 2 is 1/4 of a mole. Okay? So it's our 0.25 molarity, moles per liter, as far as the concentration. And this one is 3 grams of H2. So that's 1.5 over 3. Okay? Which is going to be 0.5 molar. So you got 0.5 molar, 0.25 molar, 0.67 molar. So which one's going to have the greatest pressure? 0.67.
Did you also just like as the smallest container or
Well, no, it all depends on how much is in it, though. I mean, if this was empty, there wouldn't be any pressure. So again, if this had been 9 grams, it would have been exactly the same as the other one. Okay, so it's all about concentration. Moles per liter. Remember, P equals mert. P equals molarity times RT. So then if the gases are mixed, it would be the one you had the most moles of, which would be the hydrogen gas to me, would be the one you had the most moles of. The rest, I think we can just kind of figure out. I think I covered all the points I wanted to cover. Okay. This one should look kind of familiar because it's kind of like the equilibrium lab that we did. And so predict whether solution become more yellow when either is heated. So if delta H is less than 0, a lot of y'all struggle with this. If delta H is less than 0, is it endo or exo? Exo. So where does heat go? On the product side. So when either is heated, so if I heat it, which way is it going to go? Towards red or towards yellow? Towards yellow. Okay? Heating is going to go towards yellow, so I can eliminate these two down here. Okay, take one at a time. Don't try and do them both at the same time. So now, diluting with water. What do we know diluting with water is going to favor?
aqueous?
More aqueous ions, which is going to be red or yellow?
Yellow.
Yellow. So diluting with water, more yellow. See, we know this stuff. We've covered this stuff.
Which one did you say diluting favors?
More, the one with more ions, more dissolved ions, more aqueous ions. And that was again right from Le Chatelier's principal lab, that you know, with pink and blue. Okay, good stuff. Good review. Okay, good review for as we're. And if you guys want to, feel free to do more review. Okay, now let's just talk now about electrolysis. How much time do I have? Perfect. Electrolysis.
I didn't get my paper. You get the top one.
Oh, never mind. Take me different.
What is school?
Okay, so electrolysis is just the reverse process. It's adding electricity to make a reaction occur. It's not one that produces electricity. We're forcing something to go away. It doesn't really want to go. Okay, you're adding the energy in. It's a non-spontaneous reaction. We're forcing it to occur. Now we have to think of electricity as like water flowing through a hose. The amount of water flowing through is current. Okay, current is equal to the amount of electrons or charge flowing through a wire or a solution. Okay? It's measured in coulombs per second, which we call an ampere, abbreviated amps. And it's simply an A with a little halo on the top. No, actually, it's just an A. A with a halo is an angstrom. A. So then we have the Faraday, which is equal to coulombs per mole of electrons. N is moles of electrons for every mole of substance. Okay, that N is just, again, how many electrons are being transferred. So if it's going from Fe to Fe2 plus, or in this case, if we go Fe2 plus to Fe, N is going to equal 2. If it's going from Cr3 plus to Cr, N is going to equal 3. Okay? Your last thing is going to be your voltage. Your cell potential, your volts. This is where I'm having a senior moment right now. I'm struggling to remember the unit on it.
Moles.
Energy per
No, it's
Joules per mole reaction.
joules per mole of coulomb. Did you see that on the like invention thing on the I said she got all the latest shit.
it's
Oh, yeah, I was like,
I said that shit.
that's not gonna be right. Come on, Steve.
every single time.
No, we're just gonna see.
Bros, baby.
So we're gonna go. You're either gonna go from time, okay, and then the only thing that's gonna have time in it is going to be current, and so you can go time to charge. So that's gonna be how many coulombs. So when we start with seconds, we can multiply by coulombs per second and get to coulombs, okay? And then once you have coulombs, you can get to moles of electrons, okay? Using the Faraday. Then you can go from moles of electrons to moles of substance using N, and then you can get to grams of substance using the molar mass. So we're actually going to be able to go both ways on these types of problems. Volts is the pressure, and it's joules per coulomb, but we're never going to have to know how to do that. Volts, the potential is how much force is pushing the electricity through the wire. Okay? And when we come in tomorrow, how much time is left? Not much. When we come in tomorrow, we'll look at doing these problems and seeing how much time does it take for the current, a certain number of amps to go through. How long does it take to deposit a certain number of grams? Or if you need this, you can go both ways. And we'll look at practice problems with this, and that's going to be everything there is in this unit. All right.
So we're doing test Friday?
No.